Oh, hello, guys. Good morning and welcome to spring in lovely Flagstaff, Arizona. So we are here doing a live stream today on the spring equinox. Of course, that's if you're in the northern hemisphere. And if any of our friends in the southern hemisphere are watching, happy fall equinox to you. So I've put together a little presentation that we can talk about the equinox, what it is, and some fun activities that you can maybe do at your home, and also the cultural significance around the world. So I'm going to share now my screen. Let's see. All right. So this is a picture from our GODO, which we'll talk about in just a little bit, the Giovanni Open Deck Observatory. That kind of shows you a little bit about the equinox. But to begin with, let's just talk about what it is. So here's a couple of pictures I took actually just this morning outside my house. So the signs of spring are definitely coming. A few little buds in the ground. The first leaf buds on my aspen tree outside as well. So it's really starting to warm up a little bit here. And also at Lowell Observatory, the hill's starting to wake up a little bit, which is really nice after a long year. We're starting to move into our phase 2 of reopening really safely. And so that's exciting to start having a few more guests up on the hill and for us to be able to be up there working. And in fact, tonight we'll be doing a Messier marathon, which is going to be super fun. If you haven't heard about that, you can go check out one of our other videos on that. But we'll basically be up at the GODO all night, imaging really cool objects with our plane wave telescope. So it's going to be awesome. So technically, what the spring equinox is the time that Earth is around the sun. That the Earth is pointed towards the sun in such a way that about half of the Earth is illuminated and half of the Earth is dark. In fact, that's where the name comes from, equinox equal night. So during the equinox, both spring and fall, the time of day and night is about equal at 12 hours, not precisely. But the reason for this is because of Earth's axial tilt. So if you'll remember that the Earth is tilted at about 23.5 degrees from vertical. And so during different times of the year around our orbit, different parts of the Earth are getting more sunlight or less sunlight, depending on where you are. So this picture really helps me see this visually. That line that you see between night and day, that's called the terminator line. So this first picture looks like it would be on summer solstice. That's when the northern hemisphere is most tilted towards the sun, and we get that lovely summer heating and weather. Whereas this bottom picture down on the left is the winter solstice for us in the northern hemisphere. That's when we're pointed away from the sun, getting less of that solar radiation. But those two images that you see on the right, they are pictures at the spring and fall equinox. And you can see that exactly half of the Earth is illuminated. So half of it is in day, half of it is in night. And the terminator line connects the north and south poles. So this is the time that the seasons are shifting, that the sun is going from being low in the sky in the winter to being higher in the sky in the summer. This is kind of the midpoint that we celebrate. So moving on, I find it actually pretty hard to understand the geometry sometimes of the equinox and the solstices. So I like to do experiments at my own house. You can see what I do in my free time. On the right, there's a picture of a little Earth that my kids and I made and a flashlight. And you can see we just stuck a little skewer through the center of it to represent the axis of rotation. And so then you can play around with that, with a flashlight being your sun, basically, and play around with going around in elliptical orbit. Make sure that you always have that pole of the Earth tilting in the same direction, and you'll see how the shadow of the sun on the Earth, the image of the sun on the Earth changes as you go throughout the year. Another really cool experiment that I haven't tried yet, but I'd like to, is from the Stanford Solar Center, is just developing your own kind of scale model for your latitude. So this one was designed, I think, at 37 degrees latitude, which is about San Francisco. So here in Flagstaff, it'd be a little bit lower than that. But basically, you trace out the lines, the path that the sun takes throughout the year on its highest point at the summer solstice, its midpoint on one of the equinoxes, and then at its lowest point on the winter solstice. And it really gives you a good idea of how the sun is moving. And you can tell on this image, and we're going to go to the next one too, that the sun actually rises directly in the east at the spring equinox and sets directly in the west. And this is true no matter what latitude you live at. And you can see on this diagram here that that's because the celestial equator, that's kind of the projection of our equator out into space, intersects with that east-west line on your horizon at this time of year. So again, that's kind of complicated to understand. But you can see some examples of how we've kind of used that fact that the sun rises east and west on the equinox and noticed that fact for millennia. As long as people have been looking up at the sky, the sun is our source of life, our source of food. And so people have marked the passage of time and the passage of seasons with the sun. And here is an example of that at Stonehenge, which is probably one of the most famous examples of a monolithic structure built to really highlight the seasons and where the sun rises at different times. So you can see that it's kind of in a circular plan where the sun will go up, will rise between those rocks right on the equinox. And we actually have a really similar setup at the Godo, which is pretty cool. So we have that same circular design, and then we have these plinths that you can see around the edges. And they line up with the sunrise and sunset at different times of the year. So you can see on the left here, I have the plinth shown that says, "Where does the sun rise?" on the equinox, I believe. And so this, you can see that the sun is rising directly through this plinth, and it's a very reminiscent of that Stonehenge effect. So we are going to move on here. And talk about some other places in the world where people have designed their architecture to celebrate the spring equinox, celebrate this time of year. So this one was taken in Cambodia. There's a temple called Angkor Wat, and was built probably around 800 years ago. And the really amazing thing about this is that the sun rises directly above this central tower right here on the morning of the spring equinox. And I was watching a documentary, actually a National Geographic documentary, featuring archaeoastronomers. And we have a cultural astronomer ourselves at Lowell Observatory, Daniel Adams, and she was the one who directed me towards this. And it's just amazing, the engineering that went into these buildings, like this temple. So the sun, like we said, rises directly in the east on the day of the equinox. But you can imagine that by the time it had gotten just a little bit up in the sky, that it would have been off to the side if you would have laid out this temple directly east-west. So they actually, the people who were building this, angled it about half a degree off of those cardinal directions in order to get this effect where the sun rises directly at the peak of the temple on the equinox, which is pretty incredible and a beautiful sight. I would love to go there. Another place in the world that celebrates this equinox phenomena is in India. And this one, I'm going to butcher the pronunciation, and I'm very sorry. It's the Sri Padmanabha Swami Temple in India. And the current building dates from about the 1800s, but this temple site has been there dating back to the 8th century AD, or the current epoch. And you can see that on the equinox, the sun appears to rise right through these windows in the center, which is a really beautiful celebration of the beginning of spring and the things that go along with that. Another really amazing site, and really one of the oldest sites that has been found, was built around the 4th century BCE. So BCE is, before the zero. And it's just really an incredible feat of architecture. This temple is called the Manajra Temple Complex in Malta. And you can see in this image here that the sun appears to rise like right through this doorway on the Equinox, and it actually illuminates the whole central corridor of the building. So it's really a feat of architecture and of astronomy to line this up such that it would go in right through this central corridor. Now, they've actually likely used the Pleiades, which is an asterism, typically part of Taurus, the bull constellation, but it's kind of a mini dipper shape, and it always arises pretty much due east. And so there are markings on the stones here at Manajra that we think represent the Pleiades, and that they used the Pleiades as a kind of an alignment to find where east was and where they should align this temple. And during the Messier Marathon tonight, because the Pleiades is actually one of the Messier objects, we'll be talking about the Pleiades a little bit more and how it's been culturally significant for many cultures throughout the years. This one is one of my favorites because it's close to home here in Flagstaff. This one is at Chaco Canyon, New Mexico, which was a major center of Pueblo culture from around 850 to 1250. And so there's this huge complex that's built kind of to align, again, like Stonehenge, like our Giavale open deck observatory, to align with the equinox. But there are also some other features that are amazing, like these sun daggers that appear to pierce spirals carved into the wall at certain times of year. So this is an example of how the sun appears to pierce this spiral, and that's at Fajada Butte. So if you ever get a chance to go there, I would highly recommend it. It's a really interesting cultural site and a UNESCO World Heritage Site, I believe, as well. Another one that's, I guess, fairly close to home here is in Mexico, which I forgot to write on the slide there, but this is Chichen Itza. So this is a site that was built, I didn't write when it was built, but it is a religious site and an astronomical site again, where they took into account the position of the sun at certain times of the year. And this specific pyramid on the site is known as the Pyramid of Kukulkan, who was a feathered snake, a Mayan snake deity. And a lot of this temple is dedicated, and you'll see images of this snake deity. But the temple, this part itself, is actually a physical depiction of the Mayan calendar. So the steps on it, if you count them all around, all add up to 365 days in the year. And the most amazing feature of this is that on the equinox, this shadow that this triangular shadow pattern from the stairs lines directly up with this slope here. And as the sun progresses across the sky, the snake appears to kind of climb or slither down the pyramid. So a really excellent depiction of celebrating the sun and the equinox during the spring. Now, so we've looked at some places around the world, but what can you see from your own home? One of the things that is kind of little known, but is a good thing to observe right now, is the zodiacal light. And you may have seen it before and not known what it was, or thought it was just the Milky Way. But it's this kind of hazy triangle of light that extends up above the horizon in the direction of the ecliptic. So in this picture, which is from Caroline Halderman, who is actually from Flagstaff, and she has some amazing astrophotography. If you ever want to check that out, you can go to her Facebook page. But she took this long exposure image from East Flagstaff, and it shows the Milky Way over here, but then this other strange cone of light, that's the zodiacal light. And so it's a good time to look at it in the Northern Hemisphere after dusk in the spring, because the plane of our solar system is aligned to the western horizon, or perpendicular to the western horizon at sunset, approximately during this time. And that light is actually coming from dust reflected off particles that are floating in the plane of our solar system. And so those are kind of ancient pieces and bits left over from the formation of the solar system, we think, that are reflecting a little bit of the sun's light and casting this faint glow that you can see in the sky there. And actually some new research has just very recently come out that suggests that the zodiacal light is actually, these dust particles that you're seeing reflected are actually from dust storms on Mars. So that's a really cool kind of connection to Mars and everything that's going on there right now with the Perseverance rover. So what we're seeing when we see the zodiacal light is the sunlight reflected off these particles that actually come from Mars. So let's see. So if you get a chance, go out in a dark sky and look for that. But in order to kind of talk about the sun, we also want to talk about time. So people, of course, for millennia have been using the sun to measure the time. They used sundials like this one seen here. This is actually the sundial at Lowell Observatory, which is really cool. This part in the center is called the gnomon. It's the part that makes the shadow of the sun. And you can see that it's actually modeled in the shape of a griffin. The names of the observatory staff are carved in. It's just a really cool piece. But the way it works, of course, is just by casting a shadow. So when the sun is highest in the sky, that's the solar noon, there won't be a shadow, or it'll be just right above where the gnomon is pointing to 12 noon. So that's what's known as solar time. And that's the way that time has been measured for a really long time. And can still be measured pretty accurately just by looking at the sky. But back in the 1800s, late 1800s and early 1900s, time changed, which is a funny thing to think about. And so before that point, every town, every place had its local time. It was measured based on the local noon of this when the sun was highest in the sky. But you can imagine as you went, from east to west, that the time of local noon changes by a little bit. And this was never really much of a problem in the days when transportation was slow, when people were walking back and forth or riding horses. There was never much of a problem. You just kind of adjust to the local noon once you got there. But once we started transiting in trains and needing to kind of organize times when things were going to get places, it became clear that we needed a standardized way to tell the time. And so in England in 1847, they were the first to decide that local time would be kind of done away with in favor of what's called Greenwich Mean Time. So if you've ever wondered why, or heard that GMT abbreviation and wondered why we measure our time off of a tiny place in England, it's because that's where they first decided to standardize the time to in order to make the trains run on time in England. In 1869 in the US, when things were picking up with the rail lines, again, it became a problem that everybody was on just a little bit different of a time. Especially, you can imagine if two trains were trying to cross each other on a single track, it would be very important to know where each train was and when they should get in the proper siding. So in 1869, an observatory in Allegheny, Pennsylvania, was putting out a broadcast, a telegraph at local noon to, kind of standardize this. And so more and more people started using Allegheny time, which was broadcast over that signal at noon time. And it caught on. And finally, in 1918, they decided that everybody in the whole US should be on a standard time that would be divided up into time zones. And so this was passed into law in 1918. And that also included the dreaded daylight savings time. So that's, in Arizona, we don't actually have daylight savings time, which is pretty nice. So you can blame it on the trains, I guess. We are all products of this Standard Time Act in 1918. And I see a couple questions that I missed before. I'm sorry. What can you see from your own home? So we're going to talk a little bit more about that coming up in the program. I have some ideas for activities that you can do at your own home. And also a question about the dust theory for the zodiacal light. when was that discovered? So that was in a paper that I just read recently. I think the information came out about a month ago, although it was from I think the Juno mission to Jupiter that data was collected. So the data was probably collected quite a bit ago, but researchers just discovered this connection to the zodiacal light. All right, so moving along. So time, like we said, has kind of evolved. The concept of time has evolved, and from being just something that you looked at your sundial locally to something that was prescribed by the government, maybe just because we need the trains to run on time. And now it's really pretty high tech, actually. So at the National Institute of Standards and Technology in Fort Collins, Colorado, you can see this series of antennas here. And they broadcast based on kind of a pulse modulation thing, the local noon in standard UTC or Greenwich Mean Time. And they do it using an atomic clock, which is crazy accurate. So that's this guy over here working on some of the technology. So now if you have a clock radio or a phone or things like that, they will actually download the correct time from this broadcast by the National Institute of Standards and Technology. So time just becomes more and more advanced, I suppose. So another effect of the way that the sun moves across our sky throughout the year is this Analemma pattern. So if you've ever looked at an old globe and you've seen this weird figure 8 on the side, usually somewhere in the Pacific Ocean, you might have wondered what that was. So we've talked a little bit about how the path of the sun seems to change throughout the year. It's lower. It takes a lower path in the horizon during the winter, and it moves upwards till it's kind of right in the middle on the equinox, and then at its highest point during the summer solstice, the highest arc across the sky. But if you were to actually just take a single snapshot of the sun at a given time, say local noon, every day or every week throughout the year, what you would see is this weird figure 8 pattern called an analemma. An analemma, the word actually just comes from the word sundial. And there's a couple reasons why the sun makes this pattern, which I think are pretty cool. So why the crazy 8? Well, the first reason, and really the reason for so many things on Earth is this tilt, this obliquity, we call it, of 23.5 degrees or 23.4 on this graphic. It's somewhere right around there. It does change very minimally over the years. But so the north-south component of the analemma, the reason that you see the sun going all the way down here and then all the way up north is because of this obliquity. And again, that's the effect that makes the sun appear to kind of rise higher in the summer into the sky and lower in the winter. So that's what gives it this north-south component. When you're taking these pictures throughout the year, you'll see the sun higher in the sky at local noon during the summer, and of course lower at local noon during the winter. Now, another reason for the weird 8, this is actually the reason for the kind of horizontal or width component of that analemma, is because Earth's orbit is elliptical. So if we were in a perfectly circular orbit, we'd be going the same speed around the sun all the way around. But because it's elliptical, we actually move a little bit faster at certain times of the year around the sun. So when we're closer to the sun, when we're getting a little bit more pull from its gravity, the Earth actually moves faster in its orbit, and then it slows down just a little bit when it's further away. And that happens to correspond, the closest time, the time we're closest to the sun, or the perihelion, is during the winter months, and the aphelion, or the time that we're going to be moving slower, is actually during the summer months. So because the sun is moving faster sometimes and slower sometimes, not the sun, but the Earth is moving in its orbit around the sun faster and slower at different times, the sun can appear to be kind of ahead of where it should be at your local noon or behind where it should be. And that's what gives the analemma that kind of horizontal movement back and forth. And we have a question from Brendan that can the analemma be observed from anywhere on Earth? Yes. So I would say at the North Pole, maybe not. But wherever you are, you can look up, and we're going to talk about some ways to actually record the analemma. and make that pattern for yourself. So here, let's see. So there's actually one more thing that affects this crazy eight that we'll talk about, but not in depth, because that's probably a lesson for your astrophysics teacher. But the crazy eight is a little bit squished, and that's because of a thing called the apse angle. And that means that our solstice doesn't occur exactly at the time that we are closest to the sun. And so that's, again, kind of a complicated orbital phenomenon, but it does add to the shape of the analemma a little bit. And actually, if you have more questions about that, I would highly recommend analemma.com. It's crazy informational. They have a lot of information on each of these things that cause the different shape changes in the way the sun is viewed at that time. So I'd highly recommend that if you're interested in more information. And here's another interesting kind of thought experiment. An analemma could be observed from any planet. So on any planet, like on Mars, if you wanted to record the position of the sun at local noon, you could do that. And on Mars, it would actually make this teardrop shape. And the reason is that Mars has a more elliptical orbit than Earth. So again, that means it's moving much faster at certain times than at other times. And Mars also has a tilt, about 25 degrees, so just a little bit more than Earth's tilt on its axis. So it creates this really cool teardrop shape. So it's fun to do that thought experiment, like what would an analemma look like on an exoplanet that had a binary system? I don't know, you could go crazy with it. I think that would be a really fun thing to do. All right, so here's some things that you can do from your own home. So Brendan, this kind of is to answer your question. There are a lot of ways to make your own analemma. So one of them is, the very simplest, is just to look out a window. So if you have a southern facing window, the path of the sun is always just a bit to the south. It's never directly overhead unless you're at the equator. So for us in the northern hemisphere here, it's always just a little bit to the south. So if you have a southern facing window, you could actually just look out the window and put a sticker on the window at local noon, say every Saturday or something like that. Now, do take into account daylight savings time. You want it to be the same time that you're doing this throughout the year. So if your time changes, you have to take that into account. If you're going to do this window method where you're just going to kind of put a sticker on the window every week or so, I do recommend that you would get some eclipse glasses to look safely at the sun, because you never want to look directly at it. You may think that's a myth, but it's not, of course. The sun is putting out a lot of ultraviolet radiation, and one of the least complications from staring at the sun would be a sunburn on your eyes. So that sounds very unpleasant, and it just gets worse from there. So you really need to use eye protection if you're going to do this project and actually look at the sun through your window. But there are other ways where, if you don't have eclipse glasses or something to that effect, that you can reflect the sun's position onto your floor or onto your ceiling, onto your wall, and record the positions there. So this is actually a picture from my house. I have a south-facing window right here, and I have this little thing called a rainbow maker, which is just a prism. And so it takes it, when the sunlight shines through it, it reflects a spectrum onto my floor. And so if every day or every week at noon throughout an entire year, local noon, I were to put a sticker where that reflection happens, you could actually trace out that shape of the analemma. But you could also do this with a mirror. So if you have a little compact mirror, you could put it on your windowsill and reflect the sun's image up to your ceiling, and put little dots to mark the position throughout the year. And again, you would get this analemma shape. But I think you could really go crazy and get creative. So one way to look at the sun safely is by using a pinhole camera. And actually trees, the pattern of the sun through the leaves when it comes down onto the ground, it creates a pinhole camera effect. So what you're seeing is not really just the shadow of the leaves of the tree. It's actually the image of the sun because of the properties of light and diffraction. So this is a picture that was taken during an eclipse, and you can see the image of the sun all over here. So it's possible that on every day, if you went out and picked one certain spot where you can see an image of the sun, a pinhole image, and marked that spot, you could also create an analemma like that. So there are lots of different ways to do this. Alternatively, you could make your own kind of little sundial here using whatever you can find as a gnomon. Again, that's that little pointy part that creates the shadow. And you could, mark a place on your driveway, say, where you're going to put this box lined up with the cardinal directions every Saturday or every other week or something like that. And you could go out and record the position of the sun, and you can see over time that you will get this analemma effect like that. Or you could use a pinhole camera in a box and project the image onto a piece of paper inside the box and mark it there. I think NASA or JPL has some really good instructions on building a pinhole camera. So in a box, if you wanted to look those up. Let's see. Oh, this one is my favorite, actually. Dr. Michael West, who's one of our astronomers up at Lowell, sent an email out with this picture the other day, and it is a around 8 years and 1 month exposure on a pinhole camera in a can. So you can actually build a pinhole camera by poking a little hole in a can and then covering one side with photographic material, photographic paper, and then setting it somewhere where it's going to record the sun's position. And so this was actually a project by Regina Valkenborg at the University of Hertfordshire. She thought she might just, take a couple images with this pinhole camera, but then it got forgotten. It was left on a telescope for 8 years and it was found undisturbed. And so when they took out the photographic paper, they were able to find this picture of the sun's paths throughout 8 years, over 2,000 individual little traces there. So that is a really cool project, I think. I have another question here. I have a sundial, but how could I tell when time has really changed? So that's a really good question. So the solar time, it doesn't change. It always is the time that the sun is directly above, solar noon is always the time that the sun is directly above you. Now, the way you can tell if that's different is by looking then at your clock time. So solar time and clock time will differ for reasons, like we said, because we've now standardized our time across the nation, and we don't go by what the actual time is at your local spot on the earth anymore. So you can, by looking at your sundial and telling the time on that, and then looking at, say your cell phone and looking at the time, you could tell the difference between your local time and the solar time. So that's a really cool thought experiment too, to look for yourself and see, how does my concept of time differ from what the sun's doing in the sky? So I hope that answered your question. And here's another fun Analemma activity. It's the basic same activity, but I like this one because it has a really old picture of our director, Dr. Jeff Hall, and his boys. So they used an old pole sticking out of the ground as their gnomon and marked the position of the sun with stakes every other week throughout a year. And they actually the kids got to paint the stakes different colors based on what season they were observing in. And you can also mark the days that are, the vernal or the spring and the autumn equinox. You can mark the solstice days and really get a better understanding of how the sun moves across the sky and how it looks at different times of the year. So I encourage you to go out and make a sundial, make a pinhole camera, make an analemma in your house. I actually think I'm going to try to do that one with my kids, with our little prism, and mark one on the wall. So this spring equinox time is a time of rebirth and renewal in the Northern Hemisphere when we're celebrating spring. And before I leave you, I want to show a couple images from the Godo. So up from the Giovanni Open Deck Observatory at Lowell Observatory, where we have those plinths that I was talking about earlier. Last year, we actually took some time-lapse images of the sun rising and setting directly in the east and west. And so I'm going to play those for you right now. So you can see the sunrise on the in the spring equinox coming directly from the east and going through that hole. And it's just really beautiful and a cool celebration. And then again, you see the sun setting, and it's a little bit blocked by the trees, but you can see that it would set directly to the west through that western plinth on the day of the spring equinox. So again, go out and observe for yourself. You can see a lot just by observing. That's the sign with a quote by Yogi Berra that's at the front of Lowell that I really like. Here's another question. What's the difference between spring equinox and fall equinox, aside from the fact that one's spring and the other's fall? That's a good question too. So the difference is whether you're in the northern hemisphere or the southern hemisphere. So for us, the March equinox, the one that happens in March, is the spring equinox, because we're moving into the time of the year when the tilt of the earth is going to be pointing the northern hemisphere at the sun. So we're moving into that summertime. Whereas in the southern hemisphere, in that same March equinox, they're actually moving into the time of the year when they're going to be the furthest pointed away from the sun. So that is their fall transitioning into winter. And now the opposite is true in September during the fall equinox. It's the fall equinox for us here in the northern hemisphere when we're going into the winter months, and it would be the spring equinox in the southern hemisphere when they are moving into the summer months. So if we don't have any other questions, I'm probably going to wrap it up here and just thank you guys for joining me here in YouTube land. Happy spring, and look forward to seeing you maybe tonight at the Messier Marathon. We'll be streaming live from the Godo. So everyone have a nice day.